All right, so we're going to talk about audio gain structure. And the first things we need to think about is, why is gain structure important? Well, and in general, with audio, good in equals good out. So that means if you give it a nice clean audio, you're going to have a nice clean audio going out. When it comes to digital signal processing, DSPs will only do what they're told to do. They're computers. The DSP is also effective when the source and audio outputs are optimized. So those are the kinds of things we need to look at and why gain structure is important. And you can see on the screen a few other nice reasons, minimize distortion and maximize signal to noise ratio. So let's go right on. And here's the basic signal flow of an audio system, right? So we have a source, different types of sources, and it enters your DSP at the preamp. The preamp's where we adjust it, and it allows us to help the signal coming in that are below the desired nominal input to increase that so we have a nice signal. Once inside the DSP, we run it through some processing through things like EQ, gain, mixers, possibly some AEC, and so on and so forth. The signal makes its way out of the DSP and heads to typically an amplifier, which in turn has to feed a speaker. Now, if this were an ideal situation, the perfect scenario, the voltage would be the same from start to finish. So that means the audio would come out, we wouldn't have to change anything. It would be processed at the same voltage, same levels, and output to the amplifier and to the speaker all at the same level with no adjustments. However, not all sources or outputs are created equal, as we know, so that's not always the case. A Blu-ray player at consumer level does not output the same level as a microphone or even a professional audio device. So let's jump right in and go over some terminology to make sure we all understand what we're discussing when we talk about gain structure. So the first one most of you might recognize, which is dBu, and that's a decibel unloaded. It's just a measure of voltage where 0 dB is 0.775 volts. Well, the way we want to look at this is that every time you add 6 dB in gain, the voltage doubles. So therefore, if you reduce it by 6 dB gain, you're halving your voltage. And when we do that, that's how we calculate up to figure out where our clipping points are and where our minimums are when we work through a system. Plus 24 dBu is the standard clipping point for professional audio. And that's very important to understand where that clipping point is, because it plays a large role in getting our gain set properly. So when we move forward, there's that 24 dBu clipping point that we can calculate out, and we could see in the voltage where it falls as we looked at that last chart. But we got to look at things like the noise floor, which is the base noise associated with a circuit. So no matter what circuit you have, there's always a noise floor associated with that circuit, and that's typically set by the manufacturer. They're going to let you know what that is. In this example, we're going to use one where the manufacturer says that the noise floor is at minus 81 dBu maximum, right? So then we take that maximum and we can figure out what our dynamic range is. And the dynamic range is the allowable signal range between the noise floor and clipping. So if our clipping point in professional audio is plus 24 dBu, and our noise floor is at minus 81, well, then we're going to have a dynamic range of 105 dB or greater. Why is it 105 dB or greater? Well, they told us the max was 81. That noise floor could be a little bit lower if we have nice, clean power coming through, through the circuits. So that's where we get that dynamic range. So that's the maximum amount of movement for your signal coming in. So when we have our dynamic range and our clipping point and we know our noise floor, we've got to come up with that nominal level. The nominal level is that sweet spot, right? That's where we want the audio to come in. It allows adequate headroom so that we don't clip, and it also far enough above the noise floor that we don't pick up any noise. When we talk about a professional line level system, plus 4 dBu is nominal level. And sound systems, when I grew up doing live, it was referred to as unity gain, right? So we think about that 0 dB. 0 dB is that plus 4 dBu, or unity gain or nominal level. Okay, consumer line level, it runs about minus 10 dBV, right? And that's equivalent to minus 8 dBu, just so you're aware. So it's a little bit less than the professional sound. And then we've got microphone levels. Dynamic microphones actually typically come in around minus 60 dBV or minus 57.8, minus 58 dBu. So it's much lower. And then you've got microphones such as condenser microphones. So condenser microphones, they're all over the place. They don't exactly have a standard level they come in. They could be minus 60 to minus 40. Anywhere in that range, you're going to have some differences when you talk about condenser microphones. And you're going to adjust those levels to try to get that maximum or nominal level point that you want by increasing your gain. So you can see here, we're building out what gain is. And right now we're still talking, we're talking analog at the moment. This is all analog terminology. So as we add to the slide, we've also got headroom. And headroom is the space between nominal level and your clipping point. And most systems, we would like 20 decibels of headroom, especially when you're dealing with music. If you get into speech only, you can actually get away with about 10 decibels of headroom. That's an acceptable level, because in speech, you're not typically going to be jumping in volume so much that you're going to clip, in periods where you're jumping past 10 dB at a time. The next one we look at on the chart is signal to noise ratio. That's the SNR there you see below. And that's the level of the input signal above the noise, okay? We want to have our input signal sufficiently above that noise floor. It needs to be high enough that we get a clean signal without boosting any of the noise from the circuitry or any noise coming into the room, right? So that's your signal to noise ratio. So here we look at the final chart of our whole system. When we consider input gain, we've got a noise floor set by the circuitry. We've got our clipping point, which is the standard clipping point for professional audio. We figure out that nominal level is +4 dBu, or unity gain, which is 0 dB when you're looking at a sound console. And then we've got our headroom and our signal to noise ratio. And these all need to be kept in mind as we're working through and first building out our system at the input side. What happens when we start to bring in the equation of digital? So when we start thinking about analog to digital conversion, you might see something called a dBFS listed. So that's decibels relative to full scale, right? And it's simply a measure of amplitude level in digital systems where 0 is the maximum possible level. So you can see here on the screen, that means our clipping point is 0 dBFS. So if 0 dBFS is a clipping point, we still need to have some headroom. So if your DSP or your sound console is actually showing you the signal in a dBFS, that means your nominal level is going to be around -20 dBFS. So that gives you that 20 dB of headspace. And it still gives you a significant SNR, or signal to noise ratio. And you still got a nice dynamic range. So we got to pay attention to what it is we're looking at as we build out our systems. Is that DSP showing you dBFS, or is it showing you dBu, right? And that's going to let you know where you want to get your level to. dBFS, again, 0 is clipping, and it's not that nominal level. dBu, 0 is really that nominal level you're looking at as you start to get into the system. So hopefully that's breaking it down a little bit, because some brands do things a little bit differently than others. So how do we go about reaching nominal gain? Well, we want to make sure we've got 20 dB of headroom in our circuit, and we just basically need to take a look at what I'm bringing in. If it's a line level, I probably don't really need to increase much of my input, right? Because I'm already bringing it in at a line level input. So maybe a few dB of increase. But if it's a microphone, I'm going to have to increase that gain quite a bit more. So what gain are we increasing? Well, we're increasing the preamp gain. So if I've got a microphone and it's a dynamic microphone, we know it's about -60 dBu. I need to bring up that gain until I get a nice high level. If it's reading dBFS, well, look at that. I'm getting about -20 dBFS. If I'm reading dBu, that's a system we're going to be looking at closer to 0. Here's 2 different examples. You probably recognize exactly which brands these come from. I pulled them from the brands that SFM carries. Here on the right side is another example of an input, and you can see the gain, and I'm shooting for about -20 dBFS, and you can see it right over here on the right. It actually tells me it's reading in dBFS. So that's what I'm looking for, is that scale whenever I set up an input, and I want to get there. Okay, the reason we want to keep this in consideration is that clipping point, right? If I take a step back and we look at that clipping point, when we talk about digital clipping, when we clip a signal in digital, it's gone. We lose our audio, right? Because clipping is created by a sampling rate. So we take a sample of an analog signal and convert it to ones and zeros, right? So that's where we get that 44.1 kilohertz, 48 kilohertz, or 96 kilohertz sample rate in our systems. So if you clip that, it's a square wave, you cut the top off, it's gone, you lose audio. We don't get that nice flexibility like you do in an analog system where you clip it slightly and it just distorts the audio. So we got to be much more careful when we talk about getting our gain set up in a digital system, and to make sure we have that headroom so we don't clip the signal. Again, if there's any questions at any point, let me know. Hopefully I'm not going too fast for you either. So let's take a look at some of these microphone considerations. So microphones have their own noise floor based on the ambient noise in the room. So when we introduce a microphone, ambient noise level in the room effectively becomes the noise floor. So if you go in and you take a measurement inside a room and you've got a really loud noise floor and you're reading 60 dB in a room, you're going to have a really hard time trying to get volume of speech in the room above that, right? Because a typical speech when we're talking somewhere between 60 and 70 decibels, right? So you're only getting a very small range. So your signal to noise ratio is very short. It's, you know, it could be anywhere between 5 and 10 dB. So you're gonna have a hard time getting a clean signal through that. So we got to pay attention to that as we build out a room. We need to have a good signal to noise ratio. We can't fix signal to noise ratio for the mic with DSP. If it's already poor, we can't take it out very well. We have some things we can work with. If you're going through AAC algorithms, they do have noise reduction, but those are, again, only dealing with things like HVAC. So if you have a poor signal, the AAC algorithm doesn't work really well, if that makes sense. So, you know, like we were talking about, if I have a nominal level of minus 20 dBFS that I'm trying to achieve, and the noise floor is above minus 35, that's really a no-go. Why is that? Well, that's because the Invictus standard is about 15 dB above the noise floor. That's what they tell you want to achieve, right? So here's how we figure that out. We have a talker start talking into the microphone. They should be a normal distance and talking at a normal level. And you're going to adjust your preamp gain while the talker is talking until you get that nominal level. If it's reading dBFS, you want to get up to that minus 20. Have the talker stop talking, and then you need to take a look at what your noise floor is. Right? So you can see here on the left where we got the big red X, it's reading about minus 31. That is that's our current noise floor, and that's not quite enough because minus 31 up to minus 20 is only about 11.4 dB. Now the one on the right shows us minus 42 dB. So that's greater than a 15 decibel difference, right? So 20 down to 42 is 22. I guess, yeah, so sorry about that. If you've seen anything jump in front of my camera, one of my kids has just jumped down in front of me, so I'll get him out of here. Don't worry about it. Anyway, so we got to make sure when we get our signal to noise ratio set up and we bring our mic in, those are the things we want to watch. Increase the preamp gain, stop talking, and make sure your noise floor isn't too high. If it is, then you need to find ways in the room to reduce that noise floor, whether that be getting the HVAC adjusted or, you know, if you got a wind coming through, close the windows. So let's jump right into a conferencing DSP signal. This is a basic conferencing DSP signal system, right? We bring that microphone input in. Typically, it's going to go through AEC, then it's going to hit some processing, probably hit a gated mixer, and hit the line output. Now, if you're using your DSP for non-conference situations and you're managing a live sound system, there's not going to be any AEC. You're definitely going to have some processing. You're probably not going to have a gated mixer, but there are other mixers you may choose from, and you still have to get to a line output. So this still applies when we think about our gain structure. We have to get it through all these different components, and we got to make sure we get the right level as we work our way through. So we're going to jump right in and start by looking at acoustic echo cancellation. If you provide a good signal to the level at the AEC, good in equals good out, right? But the reference also needs to have an appropriate level. In some DSPs, you must adjust that reference level to make sure it's the correct level to work. If you don't, then it doesn't work well, right? Things start to go awkward and you get some echo through, or it starts cutting itself out if the reference isn't right, and therefore your gain starts dropping or adjusting because you don't have the right setup on your AEC. So while most people consider AEC's got to be working right just so it sounds good and there's no echo, it can also play into your gain structure as well throughout a system. The best practice is to apply mic processing post AEC. If you do that, that's going to help keep your gain correct because you're getting the same signal in and out of the AEC for comparison when it does the cancellation. And that goes along with having a correct reference. The noise reduction, or NR, that we talked about in the AAC is only used to reduce constant noises like HVAC or wind. It's not going to reduce pin clicks or taps or coughs. Those aren't constant noises. If you increase those too much to take out constant noise, you start taking out some of the audio that you want to go through, which again can reduce some of that gain. So we want to be careful about applying too much noise reduction. Try to use as little as possible and utilize it only when necessary. Some of you may have also seen residual echo or nonlinear processing, sometimes called double talk in the DSP that you're using. And all of those, again, can help with late reflections to make sure that you don't have any echo, which can cause havoc on your gain structure as it starts to cut some of the audio out that you don't want to lose. So these are things we need to keep in consideration as we start thinking about gain. So Got a good level in, we got to make sure it's processed right going into the AAC, and that's going to be done by making sure that the level is good and has a good signal to noise ratio. As long as the AAC processes correctly, we're going to keep going on with a nice gain throughout our DSP system. And then we got processing. What about things like parametric EQ? Well, they're optimal. We need those things to make our audio sound good, right? So we think of parametric EQ, whether you're on a live console, and that's the 3 knobs to adjust your parametric. It's the same concept in a digital signal processor. You're using it to shape the audio, pull out frequencies, boost frequencies that you need to make the audio sound the way you want it to, make that microphone sound good without feeding back. Notch feedback, same concept. It's taking out very sharp notches within your EQ to keep feedback from happening. You might use fixed filters. Those are going to work on the setup of the room based on, where the speaker is located within the proximity of the microphone. And dynamic filters and notch feedback are there for when somebody decides to walk in front of a speaker while wearing a lapel mic, or maybe they put their hand over top of that podium mic. We've all seen that happen, and that causes feedback. Here's the caveat. Both these parametric EQ and the notch feedback controller can be considered gain robbers if they're not set up correctly. If you start taking deep cuts on your parametrics, or even your really wide or lots of filters on your notch feedback, where you're cutting out that audio, and we're not making up for it anywhere, so you've cut that audio out, which reduces your gain. But the exact opposite on a parametric, if you boost a lot of EQ, well, now you've put your gain higher in that frequency range, so that means your headroom has shrunk, right? So the idea is you want to try to cut as minimal or boost as minimal as possible, but you need to do the right shape to make the audio sound good. You've got to keep gain at the forefront of the thought as you're working through that, right? Keep it there. Look at your gain as it goes in and out. If you make your cuts and you look at the output meter after your EQ and it's down 5 or 6 dB, you may need to consider making up some gain on that output, right? Or readjusting your cuts so that you don't lose that gain. And then we got things like dynamic processes, right? Compressors are dynamic processing, and they're very nice. It can help you out so that when somebody yells, they don't clip the audio. They don't hit that clipping point and cause noise. So you've got to think about things like the thresholds you use when you set it up. Usually it's at unity gain, and then you can adjust ratios. Your typical speech ratio is somewhere around 2. When you get into music, probably somewhere around 4. Well, what happens when I make a deep ratio on my compressor? So if I get into start 6, where's my output? My output's no longer up anywhere near that unity gain output of the compressor, right? It's much further down. So instead of being at 0, it's probably closer to -10. Well, if I don't have a makeup gain for that and I keep that ratio in and I'm cutting the audio as it goes through, there again, I've robbed the gain from my system. So maybe I need to make up some makeup gain, or I need to test that compressor to see if I really need to have that ratio so high. So these are things you got to think about, right? Use them wisely, and make sure you're always looking at that gain so that you achieve unity gain as you go through. Then we have different types of mixers to consider as we work our way through the system. You have to choose the right mixer and understand what it's doing and how it affects gain structure. So we have things like matrix mixers, which allow you to manipulate the levels at the cross points manually. If you're a live sound guy, it's just like using your auxiliary outputs on a live sound console, right? That's exactly what it is. It's a matrix mixer. I'm assigning how much of a level for an input I want to go to each particular output. But I want to be careful of that. If I don't put enough level in, then the output's not getting the right gain. Okay, I'm only sending a low amount in. So we want to make sure that you're setting these up based on your needs of your system. If you're feeding a bunch of speaker zones, you probably want to have very similar levels of inputs, unless you're doing mix minus, in which case you may have none of a couple inputs. But again, get those levels set and pay attention to that gain so you're not reducing it through your system too much. There are different types of auto mixers. I would use a gated auto mixer in a conferencing situation, right? And it limits the number of open mics. That's really nice, because if you do have a bit of noise in the room, the only mics that are going to be open are the ones that people are talking into. So, it's listening, and this microphone A picks up a louder volume, so it opens up the gate, that audio passes through, while your other 10, 12 mics are closed, so they don't pick up any noise from the room and pass through that's unnecessary. The other one we use is gain sharing, and that's used in open discussion for sound reinforcement. And what you're doing there is you're setting a maximum gain level output. So if I say, hey, I don't want this to go above 0, that's my maximum gain, that's great. If mic A is open, that person gets the full gain. So as long as they're talking, they're going to go out of 0. But what happens if I add another microphone? Well, if I add 2 microphones, then it's got to reduce the gain of both so that that maximum gain output of my gain sharing auto mixer is still 0. How's that work? Well, it'll take mic A and mic B and reduce those both by about 3 dB. And with the mathematics and how that works out, 2 mics going out at minus 3 dB, you end up outputting about 0 dB. So then we have to reduce them all a little bit more as I add a 3rd mic and a 4th mic and a 5th mic, so that my gain shared auto mixer always outputs max level. You got to keep that in mind then, because at that point your gain is optimal going out for your maximum level, but it may reduce the gain of that individual microphone lower than you want. So you want to make sure that you're using it only where necessary. So we've kind of talked about processing. We've moved through AEC processing. We've talked about our inputs. We've got to make our way to the output, right? So we think about things like output limiting. So here we are talking about our output limiting. And the output limiting is essentially a peak limiter. If you add a peak limiter in, it's going to be used to reduce the risk of clipping at the output. If you set the limit too low, you reduce your gain. If you leave it too high, you can still clip, okay? So you got to be careful about how you set it. Essentially, you're going to want to set it around 0. Some of these come in at minus 20 to automatically limit a system so that you don't clip when you first turn it on. You don't want to forget to adjust that. If you have your level set down a little bit lower so that you don't have too much gain going out, you may want to pay attention to your output gain and increase that as a makeup gain so that you've still got your limiting, but you're getting unity gain out of the system, right? Because the limiter is going to be kind of that last stop before it heads out of the actual physical output of the DSP signal system. And we think about that, some DSP signal systems work well with their own amplifiers. In this exact example, I've got a QSC amplifier. If I'm connecting it to a QSys DSP system, well, then they're going to work together and actually manage those limits. And they have several different limits you're going to manage. You got a DAC limit, which is a clipping at stage before amplifier. And you could look at your protect, which is limiting due to drive low impedance, as well as looking at limits based on the load type. So that's all being managed through mathematics in the back end. That's measuring your voltage and your wattage and your loads so you can see what's going on. And when you have some of these, you may not need to put your own peak limiter in. You could allow the amplifier to do it. So that's a networked amplifier. But we also have amplifiers out in the world that have DSP and limiting built in. Feel free to use those. Just make sure you've check your setup as you work your way through the system and adjust those, right? You don't want to put too much limit on because suddenly your limit is really low and then you can't get the gain into the room that you need. You're not getting the output that you need, right? So that's when we start talking about output limiting. So if we get back to our DSP side and we look about output gain structure, we got to take some thought into what level do we output out of the DSP, right? So now I'm going to exit a digital signal processor. So I got a digital sound, I'm going to convert it back to analog and send it out to a system. Well, what level do I send that out at? So, well, at 0 dB, that's perfect if you're dealing with a professional sound level, right? So we're going to out 0, our clipping point is 24 dBu, I'm good. And that lets my max RMS sit at around plus 21 dBu, which gives us that plus 3 dBu that you account for, which gets us up to that plus 24 dBu clipping point. We're good if we're working with professional line outputs. We can leave our output gain, right? This guy here, we can leave our output gain at 0 because we're working with a professional line level output system, a nice pro amplifier. What happens if the next device in line, that output device, is not line level and it's a consumer level device? Well, then we got to consider reducing the output for that device, right? The clipping, we want to decrease the output gain to prevent clipping at the downstream device. So that means if I got a consumer line level that's reading at minus 8 dBu, I can't output a full scale nominal plus 4 because it's going to be too close to the clipping point. We need some headroom. So we got to consider some headroom. We reduce that output gain and we send it off to our amplifier. One of the easiest ways to check that when you're done is send some pink noise through your system and take a look at the input meters of your amplifier. If they're clipping, you're still not reduced enough, right? So even if you're not fully aware of what you need it to be, start reducing it. Take a look at the input of your amplifier and see if you're clipping it and back it down so that you're not clipping when you start hitting your maximum output levels. So that's what we talk about when we calibrate to our downstream device. With proper gain structure, You want all components in the chain to have the same clipping point, which will give you the best overall signal to noise ratio from input to output, okay? So here's that output gain structure. We look at it. Like I said, professional line levels at plus 24 dBu. And we end up decreasing our output level, as our output level decreases, our SNR decreases. So as we drop down to that consumer line level, you can see we get a smaller noise floor. And again, as we get down to microphone level, if I'm going to a microphone input of a sound console, and that's only choice I have, then I'm going to have a very small signal to noise ratio. I can't change the noise floor on the output. It is set, and that's what it's going to be. There's no real adjustment there. So, you know, when we think about that, we got to consider how we set up our amplifiers. So I want to try to get my level matched to the device that's output, whether it's consumer or professional or microphone. I want to reduce the gain of my output so that I'm matching that. Then I want to send signal to the amplifier. If I'm thinking of a concert, typically your amplifiers are going to be at full because you're going to use the full power of that amplifier to drive your loudspeakers to get those SPLs you need for a concert. But that's quite the opposite when you get into conferencing. And I've seen many cases where people just crank up the amps and they're going, I get feedback when I try to output too much, but if I reduce my output, then I'm not getting a good signal coming through. Well, no, you're not, because if you reduce your output, now you've taken the gain output way down and you've dropped it so close to the noise floor, you're probably getting more noise than you are signal, and you want a good signal going out. So instead, get that signal set at your out point, go over to your amplifier, and then adjust the gain up and take measurements in the room using pink noise to discover what exactly, to get to that level you want to be. Sometimes that's in the specifications from the designer, right? They may say, hey, this room has to reach 82 decibels. So you turn that pink noise on and you increase your amplifier once you set your output level so it's not clipping the input of the amplifier, and you increase that up until you get to that 82 dB, and there you go. You're set. Now we got to think about taking in consideration our speakers, right? Speakers play a role in output as well. So we got to think about things like the inverse square law. For those of you who aren't aware, the inverse square law states that for every doubling of distance from the source, the intensity will diminish by 6 dB. So that's something to consider, right? This is when we're talking about point source. When you get into line arrays, there's some things going on there that adjust it so you get a lot better. They still give you the specs on that on the output. So we're taking this into consideration. What we can do is we can simply take a look at our speakers, and we can go and find the sensitivity in the specifications. So this particular ceiling speaker has a rating at 1 watt, 1 meter. Its output sensitivity is 88 decibels. So I can consider if I was to measure this with 1 watt at 1 meter away with a decibel meter, I would see 88 dB SPL. Well, what if I consider a 70 volt system and I can tap it at 7.5 watts? And I found that right here at the bottom, you can see it actually gives me my transformer taps and tells me I have a 7.5 watt 70 volt tap. We see a lot of 70 volt systems in corporate settings. Well, at 77.5 watts, I'm actually going to get 96.8 dB. How do I do that? I actually went online and I found myself a peak SPL calculator. I've even found an app for my iOS device, and I can punch the numbers in and it takes care of the math for me to tell me at 7.5 watts of power, I'm going to get 96.8 dB based on an 88 dB SPL rating, sensitivity rating, right? And you can see how that increases based on our wattage at 15, 30, and 60. We're adding roughly adding a few dB each time there of our increase. So here's what we do. When we're designing our system, sometimes our ceiling heights aren't the same, or we need to take in consideration what that output's going to be. If my max output's 88 dB at 1 watt, and I need to get 82, I might be too low by the time I get further away from the speaker, down to that listening height. So here's what we do. We take some measurements. So I could say, hey, I'm going to tap this at 7.5 watts. Well, at 1 meter away from that speaker, I know it's going to be 97.8. The inverse square law tells me if I double that distance, I have to reduce it by 6 dB. So if my listening height is 2 meters away from that speaker, well, then the inverse square law proves to me that at 7.5 watts, I can get 91.8 dB SPL. So that's above what the designer has asked me to get to, so I can put it there, adjust my output gain of my amplifier until I get to the rating that I need to get, and I'm good to go. I've been in discussions with some guys recently, and one of the best things you can do is talking about having different ceiling heights. What do you do if you got different ceiling heights, but they're all the same chain for your speaker run? Well, something simple that you can do is run these calculations and then set your taps. So if you've got a ceiling height of 10 feet and you know that you're going to go down 2 meters, and that's 91.8 dB. What happens if you double that distance again and you're at 4 meters? Well, 4 meters would say you have to subtract another 6 decibels, right? So instead of setting the tap at the 20-foot ceiling at 7.5, you might have to tap that at 30 watts. That way, by the time the audio comes down from the 20-foot ceiling and joins up with the audio at the 10-foot ceiling, they're both around the same level. This is where you need to use all these calculations. So really, we've gone through gain structure. And if you haven't caught on by now, the whole point is to bring in the optimal or nominal level, that unity gain, try to keep it throughout your system around unity gain, and then set your outputs to match what exactly you need to get your output through, so that you're not bringing that unity gain of the DSP down and you're still getting a nice quality signal out of your speakers. That's really all I have for you today with audio gain structure. Hopefully I've answered some questions and helped you out so far, and I'm free to take some questions if you guys have any.
Yeah, open to any questions. Oh, Richard. Hi, Richard.
Hello. Hey, hi again. How are you?
Good, bud. Good to see you again.
Yeah, good to see you too. So this is probably a very simple thing, but I haven't dealt with it. And so if we look at the QSYS system and you have the analog and digital input gains, when do I use digital and when do I use analog?
You're pretty much almost always using analog on that system, right? Because if you're thinking about your input, the gain that you're going to adjust is from the analog, because you're sending an analog signal in, right? So you're going to stick with that analog system. You know, if you're sending the digital signal in, then you're looking at digital. But, you know, when you do that in a QSYS system, typically you're going to be looking at a QLAN receiver or an AES-67 receiver.
How about a USB input?
Yep, so in a USB input, there is a gain in there as well. You do want to keep an eye on that signal. So if the device you're outputting from is USB and you open up your QSYS designer and you go into that USB input, you've got a digital gain there, right? And if it's really hot, you do need to reduce it to make sure you got some headroom, right? And you want to get around that minus 20 dBFS, because QSYS does use dBFS on all their inputs. So that minus 20 dBFS in QSYS is kind of our unity gain, if we think of it in the old school, you know, live sound concept way where we learned, right? We're all about get that unity gain, get your faders up to 0 so you have room to mix the signal with, right? If you have it too low because your actual input gain is too high, your trim is too high, well, then you're mixing with, you know, about this much fader on your console, right? Or you've got your speakers cranked way up and you don't need it. You're still mixing with this and your master outputs are down. So the idea is get everything to that nominal level, make sure your outputs are adjusted, and that gives you room to play, whether you're in a live aspect. And if you're in a digital aspect where you're working with a conference system, it's built straight through and you've got the headroom so you're not going to clip and you're not stuck with dealing with low level audio, which has risk the increase of bringing noise in. But yeah, on that input for USB, you may have to bring it down a bit if it's too hot, which typically I do see a lot of that, even on VoIP lines.
So maybe I missed something. So if you look at input number 1, which is analog, correct? Yep. Why would there even be a digital setting if the input is only analog? What am I missing?
Yeah, I mean, you don't really ever play it. It's there for you to see what the digital signal level is. You know, that's a good question. I'll do a little more research on what the aspect of that one means. I didn't dive too much into that in my research building this because it's mostly focused on bringing that analog signal into a system and get it set up right. But I'll see if I can pull out their specs. I have some documents that I could share with you that talk about how they built the circuitry of it and why they're showing you the digital gain there. It's just to give you an idea of what's happening.
So if I have an analog signal coming into input 1 and I change the digital trim, there should be no change.
Should be no major change to it now.
Theoretically.
Yeah.
Okay. That's it. Thanks.
Awesome. Anyone else out there have some questions? Is everybody already a gain expert? I hope so.
Maybe they're all having a nap.
That could be good too. I keep looking to my right. That's my second screen, guys, so I can see if there's anybody, you know, opening up, popping a mic or a camera open.
So let me just check. Sorry, Andrew, I just dropped off. It's been a hard day, internet-wise.
Yeah, no worries. My whole power dropped yesterday in a mid-call with one of my fellow coworkers.
Yeah.
So that was always fun.
It happens.
Thanks, Steve
any
Klotz. I appreciate that.
So, Andrew, I just had a question that came up. What are some of like lately, what are some situations with audio gain structure that you've been encountering with clients and projects? And what are some things that are coming up?
That's a good one, actually. You know, when I first got into collaboration, and that's where I see a lot of gain structure issues. You know, I've worked with a lot of guys that maybe don't have experience in sound. They're programmers, and they're great programmers, but their audio background is very limited, and they don't have maybe a training in sound, so they don't know where they set gains. So a lot of things I see is just a poor level coming into the system. So, you know, you take a mic and you turn it up a little, or with digital mics, we're sending it in, and we're not adjusting the level of the microphone to that nominal level. We're not getting up to the minus 20 dBFS or in a different DSP that, you know, 0 dBu or plus 4 dBu, depending on how they've got it set, right? So if you don't get that gain come in, you're working with a level that has more noise in it. So I go into a system and people complain, yeah, you know, I've got the mic coming in, but I'm hearing a lot of noise in the output. So the first thing I do is I take a look at that input gain. And if they haven't increased it, you know, then I'm going, okay, well, you're bringing in a low level. So that's interesting. Let's go through your system. Well, about halfway through the system, I'll find a gain block somewhere where they're controlling the level, you know, and that'll be boosted up 6 dB. And then I'll go to a matrix mixer and I'll see that they boosted that signal again 3 or 4 dB. And then I'll see it right before the output boosted 5 or 6 dB. So when we think about this, I've taken a microphone signal that's come in and I've said, it's not great. I've got some noise in it. Well, what happens when I increase that audio? Does the system separate the microphone from the noise? Not really. So you're increasing both. So to get the level of the microphone you want, you also have to increase that noise. So I've increased it 6 dB and then 3 dB and another 6. I'm at 18 decibels of increase to get my mic where I want it, but I also bring that noise level up 18 dB. So if we don't get our microphones into the system appropriately, then we're trying really hard to get a level that we want, and we think we can make it up in our processing, but we're increasing the noise that comes with it, right? So that's really where that signal to noise ratio comes in handy, and making sure that we've got it set. Some of the other ones I see is over compression and then not making up that gain. So we really compress it, and then I've got this really low level output. So maybe I increase the output at the very end, but I didn't do it right at the compressor to give myself the gain, bring it back up to that nominal level through. Those are the things. And it creates a roller coaster wave when you go +6, +3, +6, you know, you're going uphill, but then I'll see a major drop because it gets too high. And I like to call it that roller coaster effect, where the gain comes in, then I shoot it up the hill, back down, back up, back down. And it's people go, oh, I'm clipping here, but I'm not clipping on the output. And if you start looking through the system, if you got that roller coaster effect, then you're going to have a real hard time getting a nice quality signal through, because your gain's so up and down. So you really do want to get that straight line effect. Try to go for that ideal 1 volt in, 1 volt through the system, 1 volt out kind of concept.
Gotcha. Thanks. Does anyone else have any questions? What I'm going to do, if there's no questions coming through, feel free to unmute yourselves or turn on your camera if you want to join in and ask one of your questions. In the meantime, in the chat box, I'm adding a link to the tag group's landing page on the SFM website. And it's a good resource to bookmark in case you ever have programmers who need some audio training or access to resources for, you know, if we're not hosting a webinar, there's a slew of links that in there that you can access our different suppliers' trainings. And also there's the tag.sfm.ca landing page, which is a support that brings you directly to Andrew or Max St. Jacques or anyone else on the tag team.
Yeah, guys, that portal is actually really nice because you're going to find a lot of FAQs in that portal. Some of them are links to FAQs from brands that SFM carries, but others are written by myself, Mark St. Jacques, and the other tag members. And they're things that we've come across, and they will sometimes involve multiple brands or things that we've discovered based on conversations we're having with people out there. So they may be brand agnostic tips as well when it comes to networking or other devices. So it's a good spot to start. And you can always jump to the manufacturer's website, FAQs as well, if you don't find what you're looking for. And you can email us directly from that page.
I'm just having a comment
Yeah.
coming through. So I guess another way with CD, Blu-ray, iPods, etc., is to have a short sample audio of 0 dBFS files that one can set analog inputs to indicate -2 or 3 dBFS.
Yeah, you could do that if you send 0 dBFS. That's that's going to be your clipping point. So you're going to want to be careful that you don't send it through a complete clipping. You'll know where your clipping level is. You'd probably want to get it to the -20 dBFS to get that nominal level set through.
Jim, does that answer your question?
Does that make sense? Because 0 dBFS is clipping.
Yeah.
Perfect.
All right. Great. Thanks. So that's about it. If no one else has any other questions or pop quizzes for Andrew, I just want to thank everyone for joining us on today's webinar. That was great. Thanks. I know it's Friday. Everyone, it's the end of the week, so your time is very much appreciated. And thank you, Andrew, too, for hosting this. We hope to see you again soon.
Thanks for joining us, guys and gals.
Thanks. Thanks, Steve. So everyone have a great weekend. Stay safe and see you next time. Bye.
Bye.